sequence for f and g are really not exotic. It's kind of, f goes, like 0 goes to 0, but then 1 goes to like 1, and then 2, 2, and then 3, 3, 3, and then 4, 4, 4, 4, and then blah. It's a sequence that you look at and say, okay. And g is the same sort of thing. It goes 0, and then like 1, 0, and then 2, 1, 0, something like that. And you go, oh, okay. These functions we know the crap out of those. And we do. But hey, if we write our number like this, index of the triangle number, overshoot it, minus a little bit, then, this one. Yeah. Then what were those two observations we made about triangle numbers? We said if our number is a triangle number, in other words, if this little extra part is 0, then this thing is just f of n. And that other thing I was saying, if it's a triangle number minus 1, then this guy is this f of n plus 2. And then an exception when n equals 2. Where that rule doesn't work, but the other ones do. So that's a kind of nice pattern. I see what you're saying. You're trying to say, if we know, say, g and f, then maybe we can relate them back to, oh yeah, and looks like it's true. But GPAT, you only did say g equals 0 and g equals 1. That's true. But then you say, you know what, I really wish I had some more data on my hands. So you get that data. And you try to check this rule. You say, well, if I can write, maybe I can write it as something like this. This one. I would work in a linear way, but I'm trying to not erase the more important things. And the hope is that P of n would equal, say, this little f of n, which says, oh, the maximum element that you need to throw in there anyway, plus some function of g of n. I don't know, I blanked on this. That looks so impossible to read. Can you really read that in, say, the back and the sides? Huh. This would be a hope. That what is it? It only depends on f and g, which that's clearly it only depends on what f and g are, because if I tell you f and g, you can figure out the number. But hopefully it depends on this nice way. It's what f is plus some function of g that, say, doesn't change once you change f. That would mean, well, yeah. If you say, look over here, it's f of n, and then plus, oh, nothing, because if g is 0, then you're good. Or it's f of n plus something because g is 1. Or f of n plus something because g is 2. Or f of n plus something that depends on the fact that g is 3. But we can't really reasonably hope that this is true always. So maybe you hope that it's eventually true. Why do I say eventually? Because in the baby examples we already worked out, this sort of formula straight up doesn't hold when, say, n equals 2. Because it doesn't. This would predict 4, but the real answer is 2, and you say, dang it! So this hope that it will look like that certainly isn't true. But maybe it's true eventually. Whatever that means. Which leads you to this experimentation. Is this the case? If so, can I find this function? Experimentally, yeah, it really does look like this is the case. That if I give you a number, it only depends on this. Let me rewrite this in a very more suggestive way. Wait a sec. Yeah, I thought of a better notation for this. I'm going to call it Q. Cool. Hopefully that's true. I'm great. And experimentally, you run the algorithm. You get up to, say, n equals 30,000. And it doesn't look like, if it's true eventually, this sort of formula, it doesn't look like it panned out quite as well as it should have. When we get up to 30,000, we did not work out the kinks yet. So if it is true, then this eventually, that this sort of formula, what is Q? I don't know, but it's something that hopefully we can get our hands on pretty nicely. If it is true, then hopefully it'll work out, but eventually is at least bigger than 30,000. And you say, crap, if I'm really going to believe that this sort of conjecture is true, and I get all the way up to 30,000, and it looks pretty darn true. There are like a few sporadic examples, and they're really far apart where this formula sort of thing doesn't work. But hopefully it'll pan out eventually. But you got to push the computation more if you're going to try to say it as a conjecture. Otherwise, you don't even have the computational stuff to back it up. So that's one aspect, and the other aspect is you also believe this is true.
So what is Q supposed to be by the condition?
It has a very strong interpretation, and I'll just give you this. You think this is true. Q makes sense. It's a thing. I'm not going to talk about it. But you think this is true. It's essentially the same thing, but instead of minimizing a perimeter, oh goodness, Q tries to minimize the perimeter of the complement. So Q minimizes a perimeter of a complement, P minimizes a perimeter, and it makes sense that this should be true. What this would then mean, if you care about the structure of the sets, it would mean precisely the best way to make the set, if these equations are true, which they're not. But hopefully, eventually they are. But this would mean that the best way to make your set is first fill it up with 0 up until you just made it too big. Fill it up with as much stuff as you need to, and then take away whatever is left in the best possible way. And what's the best possible way to take stuff away? Well, that's to fill it up with whatever you need to, and then take away, in the other sense, the best possible thing. So it's a very self-similar sort of thing, and this would be nice if it were true, but it doesn't look like it's, it looks true-ish, but not, certainly not without flaws. And why is it eventually so big already? Plus, we rented a room. We were asking the computer to hold, over a gigabyte of stuff, just for our lonesome little thing, and then randomly access random parts of this table. The probability, if nothing else, that it's going to grab the wrong thing is pretty big. You don't want to do that. Plus, it won't complain if it does that. You'll just get the wrong answers, and you won't know why.
Well, I was just thinking the eventually should depend on the K, right? The thing in
Yeah, one would think. Certainly would. It eventually would depend on that. But hopefully, you could get one independent of, say, this G. This eventually would depend on this excess little part. And if that's all you're trying to say, I nearly proved that without a good proof.
Yeah.
With a lot of hand waves at one point.
Right.
And I said, dang it, I gotta nail it down. How do we do that? Here's how. Give me a sec. You get step 1 to try to work this eventually out. The goal, hopefully we can prove these two equations are true eventually, and also figure out what eventually means. That's the goal, because the equations are nice. And if they are nice, then as far as this algorithms of how to compute stuff, this would shoot us straight to the moon of essentially instant. You could figure stuff out instantaneously in something like log time, but I think it's closer to log star time. Something really just phenomenally quick. But gosh, how are we going to figure that out? Step 1, get a lower bound for this P and Q ignore. Step 2, get an upper bound. That's just true depending on n. You can do that. If nothing else, you use the upper bound that those other guys got, or you do your own thing because you're your own person, whatever you like. You get an upper bound, not a 0. You have some bounds, and that'll tell you, okay, it's pretty true. Step 3, you use, I erased it a long time ago, you use that idea that Mikhail was talking about, You can get a recurrence relation. You can get one recurrence relation by this sort of auxiliary function. You can get a different type of recurrence relation that's based on this idea. The recurrence relation goes like this. I'll say it in words. Here's what we're going to do. We're going to condition on the maximum element of our set, which is going to come back to bite us, but turns out it helps in the analysis. Conditioning on the max element of the set. And we're going to say, the best way to make a set of volume n is make it with maximum element m, or whatever. That's going to change, it's going to vary. And then do the best you can. But to do the best you can, given what the maximum element is, you can write that in terms of, well, it needs to look like this. Then we need to kind of take away stuff. Because if the maximum element has to be m, then the set needs to necessarily look like 0 up to m, and then what you take away, and then you can write some stuff, there's some minimums. You can write these p and q's in terms of each other, but it's a minimum over infinitely many terms. So you can't use it to compute stuff because it's a minimum over infinitely many terms. When would you stop? You could try to use it to compute stuff and figure out when to stop. It doesn't speed up the stuff that much. But so yeah, you get this other recurrence, it's infinitely many terms, but it looks a lot nicer. It's really compact. Then you push real hard to prove that this other recurrence that has some minimums, blah, 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 you prove that these are true eventually because of some analysis. Analysis says that eventually is about 3 million. Because you're not that good at analysis, and you don't care that much, because you said, that's okay, if I can get eventually, then the computer can help me figure out the rest. But analysis land says, yes, this does work. So instead of a hope, it becomes, say, a theorem that says eventually, but eventually is 3 times 10 to the 6. This is true. And you say, cool, but that result does not sound as good as this is true, except for these counterexamples, which is kind of what we're at. If I say, here's a fact, P and Q are this, and I give you some initial conditions. No problem. If I give you these initial conditions and I say, it does work out if it's big enough, then you say, oh great, so all I have to do is check when it's small. And when it's small, I'll see this will probably work out anyway, but you know, we'll just put a good table of where the exceptions are. But like I said, we were able to get up to 30,000 earlier because we very legitimately ran out of memory, and it was rude of us to expect the computer to hold on to all that stuff. So that's like a for real problem that's not going to get solved by doing something in a more clever way or by doing something in a different language. It's going to be solved by doing something, well, in a more clever way, the first thing I said. It's going to have to be solved with a hopefully you can push it. At this point, I emailed Dr. Z, and I said, Dr. Z, hi, you don't know me yet, but my name's Pat, and I'm working on this problem. And I got this thing, and I have a result that holds after like 3 million. And all I want to do is check between 1 and 3 million, but I can only get up to like 30,000. And Dr. Z said something like, don't worry about it. In 15 years, computers will be able to do whatever you can't do right now, and just wait then, and then you'll have it, and you won't have to do any more work. And I was like, okay, but I was young and ambitious, so I was like, I'm going to do it anyway. So I pushed and I pushed, and here's the thing. Turns out, fun fact, I don't know why this is true, and this would be one of those future research sort of things. What I needed to do to make this recurrence that does take this long, which isn't, the speed isn't the long thing. If you run it for like 2 weeks, you'll be done. But the memory is the hard thing. You run it and it just simply runs out because you're asking for a lot. You're asking for like n squared memory, which is unreasonable because you want to get n up to like 3 million and change for safety. And you need to remember n squared. Turns out, fun fact, this p of say nk, looks like, this is one of those experimental statements that I haven't even done anything with because, I don't know, I didn't find it particularly interesting. Looks like it only takes 2 finite values as k varies. So all you have to do is remember what those 2 finite values are, and then you can shut down your table from like having to remember n times k things to just like n times 2 things. Of course you like hedge just in case you need to remember more, you allow that to happen. But it turns out that you didn't. You only needed to remember like 2 or 3 things. For any fixed n, k really just didn't do that much, which was surprising. But that saved the day. I cut down memory from n squared to n. You push it up to 3.5 million for safety, and then you're done. So you do get that this is true, and you don't have to say eventually, because eventually sounds stupid. You say it's true, except for 177 counterexamples. The largest of which is just a hair shy of 150 million, or thousand. So yeah, that's that. That's the story. Experimental discovery. Questions?
Yeah, this 177 is a finite sequence.
Yeah, and it isn't Sloan.
Is it long?
But they're all over the place. If you want, I can pass around, say, this sequence. Here it is. I also have some nice pictures of what P and Q look like. And I also have this sort of triangular array of P and Q. That makes a lot of sense. If you look at this triangular array, you realize that this recurrence relation, which maybe you don't like right away, if you put it in the right triangular array, you say, oh wow, that's a really natural recurrence relation.
Who put the P of N in OEIS first? You?
No, the other guys.
Okay.
But they only had like 20 terms because they were
Only
doing
20?
they were doing something not that smart.
What's the minimum you need to put it in OEIS?
I don't know. It depends how interesting it
No,
is.
five.
Like Mersenne primes, they only have however many, but they're in there. Or Fermat primes, they're for sure in there. Or perfect numbers, anything interesting enough. Especially if it's really interesting. You say, whoa, how come there aren't that many?
But these exceptions you put.
Mm-hmm. And I cannot make heads or tails of them at all. Not
Can
even
you put that in the OEIS?
I did, and yes, you can. It's weird. The exceptions don't make sense at all.
Why should you expect them to make sense?
Why are there 177 exceptions? Why would you expect exceptions? I would expect it to make sense because what I did, I feel like I did something a little bit cheating.
In the beginning, I mean, why does 3 million bother you as a limit to when junk stops?
If it's going to be junk, I expect it to be, like if it's really limited, it can do anything at once. Like if there are like 3 or 4 exceptions, I say, I don't care, do whatever you want. But if there are 177, I say, well, it's a bit too much. This feels like a conspiracy, especially if they all decide to stop. I got nothing.
What are these exceptions to, exactly?
They're exceptions to this recurrence relation. This mutual recurrence relation, F and G they're like less than square root of n, they're square root of 2n. So this is in fact a recurrence relation. You can define both of P0, Q0 to be 0. Probably, I forget. And yeah.
So is the difference way off?
Between P and Q? Or between...
For those exceptions between like the actual...
No, it's off by like 1.
So the largest is a few million?
Was that?
The largest?
The largest is 150,000. Just shy of that. The largest is, well, it's floating around, but like 147,000.
What's the small?
0 if you want to count that. 2 if you want to count that. I think 1 might be, I don't remember. 2 is definitely an exception. I think 0 or 1, I don't know. What's the biggest error? The biggest error? Oh, that's in there. That's in there. Because if you say to yourself, forget the fact that there are exceptions. Let's pretend there aren't exceptions. We'll define new functions, P squiggle, Q squiggle, and they're like the idealized P and Q that have no exceptions, and just go ahead. That would have an even more natural recurrence, because the recurrence is really natural, actually, if you look at the array. But the exceptions are not natural. But you do the P squiggle, Q squiggle, whatever, then your P and Q, they only differ from this like idealized thing by like 4.5 or something. So it's really regular. If you make it the regular version, then it captures all the shape. It just has this tiny little constant band of 4.5 fuzz factor, which doesn't really matter when you're holding it so far away anyway.
Can you generalize this problem in some ways? Can you generalize it in some natural ways?
Yeah.
And still use same techniques?
I believe so. For instance, probably a very ambitious generalization would be generalize the concepts of volume and perimeter, but that's already the name of the game, and you could probably turn it into solving the Riemann hypothesis if you generalize volume and perimeter enough. So that doesn't really make sense, perhaps. But if you change where the universe of where your sets live, if you allow negative numbers in your set, you can still make sense of volume, which is hopefully over a finite set, for instance. You can still make sense of perimeter, again, hopefully finite. Which is what they did in the original paper. Turns out that's a lot easier, and you're able to get an answer without that much work, which is pretty good. You could generalize it to say you could throw out 0, or you could say you're not allowed to use 2, or 3, or 5. I think that if you make it any subset of the positive natural numbers, it'll work out. In the sense you'll get the same sort of thing, and the exceptions will just be a different list of exceptions. I think that's what would happen, but I haven't worked on that at all. Or you can make this your favorite sequence, like the Fibonacci numbers. And subsets where you're allowed to use only Fibonacci numbers, maybe you can use them multiple times if you want, or powers of 2. No, that's stupid. Don't use powers of 2. Or something like that. And you say, oh, volume, and then maybe perimeter would be if the next term in the sequence is missing or not. I don't know, you could do something like that.
Could you do a boundary of a set of lattice points?
Sure. I don't know if that one would work. You could, push in the same manner where you try to get some lower bound and upper bound.
Like
Hopefully they're close enough.
Like it has holes in it and stuff.
Yeah.
So with this using arbitrary integer sequence thing, would you define the boundary in terms of the integers or in terms of the subsequence?
Probably make more sense in terms of like a subsequence. Like if you had the Fibonacci numbers and you had like 3, 5, 8, 8 shouldn't, or 5 shouldn't be in the, That would be my guess.
Do you have like an interpretation for what the volume and the perimeter are in other contexts? Like, did you make any connections with maybe other problems or?
Nope.
Can't you fill in the integers with intervals and think of it that way?
Yeah.
Put an interval between each integer, then it would almost be the regular boundary.
Okay, any more questions?
Yeah.
And questions will be glad to answer in private. Thank you very much.